Look at this stadium. It's tense under the floodlights during a high-stakes one-day international match between India and Sri Lanka. During this game in Nagpur, two Indian batsmen batted together to score a combined total of exactly 176 runs. We know their exact combined total, but the records here leave out one crucial detail. We have absolutely no idea what each individual player actually scored on their own. Did the first batsman score an even 100, leaving 76 for his partner? Or maybe it was a tighter split, like 80 and 96. Simple arithmetic cannot give us the answer. Because we have two unknown variables at play simultaneously, we require a different mathematical tool to track all of these potential realities. In earlier algebra lessons, problems were straightforward because they only contained a single unknown element. Take a look at this textbook excerpt showing the equation 2x plus 5 equals 0. Solving for x locks down a single answer, -5/2.
This unique solution is mapped as a single immovable point planted on a basic number line. But our cricket scenario has two moving parts. You cannot lock down two varying scores to a single point on a straight line. The old methods fail here. To solve this, we translate the real-world mystery into algebra. Let's assign the letter x to represent the unknown score of the first batsman and y for the second. When combined, we get the foundational equation for our mystery. X plus y equals 176. We expand this into a universal algebraic template. By moving the 176 over, it perfectly fits the standard form of ax plus by plus c equals 0. The textbook confirms the structure, noting one vital condition to make it work. Coefficients a and b cannot both be 0, otherwise our variables vanish. This format is powerful. It allows us to compress a complex, unpredictable event on the cricket pitch into a single, clean line of logic. To see how we extract actual solutions from this type of equation, let's use a slightly simpler textbook example. X plus 2y equals 6. Solving these equations requires choosing a starting value for one variable. Once that's set, the internal logic of the equation dictates exactly what the other variable must be. If we assume x is 2, a balance scale tips. To keep the equation balanced at 6, y is forced to equal 2. Let's try another assumption. If x is 0, the math dictates y must become 3 to maintain perfect balance. Here is the textbook walking through that exact process. This method generates multiple valid coordinate pairs, like 2, 2, 0, 3, 6, 0, and 4, 1. Finding a solution is no longer about hunting for one isolated answer. It is about generating pairs of numbers that perfectly respect the relationship defined by the equation. So if we can just keep guessing numbers for x, how many valid pairs of answers can an equation like this actually produce? This line in the textbook reveals the mathematical climax. There is no limit. A linear equation in two variables has infinitely many solutions. To make sense of infinity, mathematicians map these coordinate pairs onto a two-dimensional grid known as a Cartesian plane. Each individual solution pair becomes a dot. As you plot more and more of these possibilities, they connect to form a perfectly straight, unending line. Every point on this line represents a specific, valid solution. In effect, the graph serves as a visual map of every possible reality allowed by the equation. Which brings us right back to our original cricket equation, x plus y equals 176. That equation is a line, and that line maps out every valid combination of runs those two batsmen could have possibly scored. This exact mathematical logic scales up perfectly to encompass the massive, high-stakes real-world event playing out on the pitch. In this context, the goal of mathematics shifts. We aren't searching for one single answer, but rather mapping the entire range of valid combinations. Now it's your turn to apply the logic. Can you find one valid coordinate pair for the equation 2x plus y equals 7? Drop your answer below.